Okay, excuse me, we're gonna have one more crack at this. And so when I changed this to micrometers, one over micrometers, and in fact, it's micrometers to the -2, but the important thing is that yeah, because it's micrometers squared, so that's minor. That doesn't change anything except this bit. Okay, and so in fact, I'm not certain it has to be in micrometers, but to make sure things come out right, we're going to leave it there. So here, it actually, and I said, is it in nanometers? It's not. It is in micrometers because 740 nanometers would be 0.740, just like we see right here. Now, the further analysis video that I recorded in the past expects it to be expressed as angstroms. So I just multiplied each of them by 10,000. And it's lame, but I'm tired and I've got a whole video I made that's perfectly fine. And now these energies are reasonable, but see here I've written down the actual wavelengths here, and they are kind of off. But this is because this data was also made without getting the minimum angle, and so we never got it that great. But in any event, this is just so it plugs seamlessly into the already existing analysis video. Okay, I'll save this here. So part of this is we need some constants. And so we have Planck's constant in joule seconds, and then in EV seconds. I don't remember if we're going to use that or not, because yeah, I forget why I put it there, but we'll notice in a minute. And we need the speed of light, so it's nice to have them just here waiting. So now what we do with the hydrogen is all we have are colors, and then we go ahead and we measure angles, and once again we change it into decimal, and now we use our Phys equation up there, and this is nice because the way we set up the graph up above, the slope is and the y-intercept are directly applicable. And pause for a moment. I'm back. So we're trying to investigate this equation here on the right, and the idea is that if we figure all this out correctly, then we should be able to figure out what E1 is, which is the energy that it takes to remove an electron from the energy level 1 all the way out for a hydrogen. And so we're kind of like examining the hydrogen atom, and basically, because what this did is that it led to this other equation that won Niels Bohr a Nobel Prize. And by the way, the number is 13.6. See the n equal 1 level there. And so he came up with equations 4 and 5 at the end of the day. And z squared has to do, that is, if you wanted to look at it, something that an energy levels for a different atom. So in the case of helium, equation 5, you'd put a 4 there. And no, number of protons, so it's 2 squared, yeah, you get a 4. And let's see, singly ion, yeah, I don't know why that's there, because what we want to do is we want to do this for hydrogen, and hydrogen Z equals 1. So it's a very straightforward equation. We can rearrange that one like this. And so this is convenient because once we get everything right, this E1 should be the same for each one of the lines. And that's what we're looking for. So let's take a look here. So the measured energy divided by 1 over n final squared, 1 over n initial. And this is weird. I don't know why it says 0.25 here. So we need to change that to 1 divided by n final squared. There we go. All right. Now, what have we got here? And so, yeah, what's L17, JKL? I just decided to look at, so I took the actual wavelengths, so this would be the expected angle. I don't believe that that's necessary. This is just me playing around, trying to understand what I was doing. So we have a couple things we can do here. We can check and see how our calibration does, actual energies and the energies that we came up with. But at the end of the day, this is what we're aiming for. So this is, I took the wavelength, the actual wavelength, plugged it into the HC over lambda. Again, get the energy, and these are in electron volts. And I have my formula here, and it's just 2 pi, it's really weird. What the heck? It must have happened with some copy process. So 1 over this one squared, close the parentheses, and now let's go here. Okay, now, so we have our numbers, and one thing we'd like to know is what is the variation of these. And this is actually the range, the max minus the min. It's not exactly the variation. What we can do is, and let's see, so that's a pretty big one. But we should really look at the standard deviation of the sample. Hold on. Wow, so surprising how far behind I am in the analysis. I thought I had this analysis pretty much down pat, but always learning something. Oh, look at this. Jenny packed me a couple of chocolate truffles in my lunchbox. Ooh. Okay. So, anyways, remember these E1s should all be equal to the same thing. That's nice because, the lights just went out. It was a timer, I guess. Because then we can calculate them over and over again. We can take the average, and then we can take the standard deviation of the sample. And then we can get the standard error. And I didn't use the count function because there's only 3 measurements, so I put the square root of 3. All right. And then we have the fractional error. It's just the standard error divided by the average. I didn't multiply it by 100 because I just told Excel to format this as a percent. See up here. And I did the same thing over here on the right. Now, thing is, if we get the levels correct here, and so your lab manual shows you possibilities here, and of the transitions that we're checking out. So it's a question of, first of all, the final is always going to be the same. And so we have to just try out different sets here. And notice what I've done here. See that it updates over here. And so you have to play around with what are the sets of numbers here. Hold on. All right, I'm back. I've been a stinker. I've covered over the right answers. So the expected value of E1 is 13.6, and you see it in your lab manual. And so, not surprisingly, when I plug in the actual wavelengths, and I use the formula there, and I plug it into my E1 equation, I get over and over again 1.36. It has a small amount of variation. You can't see it here because the number of decimal places. Oops, that just means there's not enough room for the number. Okay, so ever so slightly. It could be a rounding error, but at the end of the day, down to 1/100th of a percent, this is 0. Let's see if we add a 4 1,000ths of a percent, pretty small. Now, in the actual data, I notice I have 5%, and that's not so bad. So what we'd like to see now is, though, the percent difference. Yep. And so that's not so bad. Let's see, I can get rid of the times 100. And then I could just tell this to be a percent. So, well, yeah, but 8% difference. And my error bar is only 5%. So this is an example of precision and accuracy. I have a precision of 5%. So my darts are close together, but my average value is off 8.5%. So that means that there's some kind of systematic error. And yeah, yeah, this is not percent error, this is percent difference. And I remind you, the formula for that is the absolute value of the difference between the two averages divided by the average of the two averages. We've seen it a million times. And then you multiply by 100. Okay. So once you've got all this framework, you experiment with the NF and NI values. Remember, the NFs will all be the same, so it's just a question of figuring out what well, you try 1, 2, 3, 4, and then for initial, you try if you started with 1, then you if you start with 1, then oh gosh, ate my truffles too fast. So if you start with 1, 1, 1, then this will be 2, 3, 4, and then 2. And well, I assume it's 3, 4, 5. Certainly, you might try 3, 4, 5 with 1, 1, 1, and then maybe 4, 5, 6. And basically, so next will be 3, 3, 3, like we had. Well, of course, you see that one is wrong from the next page. Some combination like this, okay, 3, 3, 3, it could be 5, 6, 7. And so basically, the way this is set up, when these become 13.6, you're done. And in fact, what we could do is, there's no real reason to keep this in scientific notation, I suppose. And we have to go back here. It's a little bit easier to see. If we we just make this a regular decimal number. And there you go, 13.6s. Yeah, look at that, I got close here. One of them anyway. 13.56. All right. Very good. So while we're here, in our final logbooks, we have our two tables. This slope estimation was just something I used to help me with this. You can actually just type in numbers there. What this is, I just took the two endpoints and did a delta y over delta x of the two data points on either end to give me a start number for the slope. And, of course, once you do that, you have to monkey around with the y-intercept. But, and let's see, 17,000, huh? It sure doesn't look like it's going to be 17. Oh, well, right. Notice that one thing that's different here, notice that this one here doesn't start at 0. If I did that, which is standard, yeah, the graph is kind of funky, right? It's not very easy to interpret. So that's why I changed this to 230. And now you have a very nice graph to look at. So this one is a little different. I let the y-axis be normal, going from 0 to something. So basically, you don't want to have a graph that doesn't start at 0. In this case, we can get away with it. One thing you would have to say is if I was graphing several of these, I would probably, one way we could do this is we could, since the angles don't mean anything in particular, we could easily just subtract 230 from each angle. And in this case, it's not a big deal because these angles mesh with each other, meaning like we didn't move anything around when we switched to the other tube. So there's no particular reason to subtract 230. But if we'd wanted to compare a bunch of measurements from different people in different times, then we'd want to sort of shift everything. Maybe the first data point is at 0. But it's not necessary this time. Okay, so final logbook part, the Balmer part of final logbook is our tables, our fit parameters, our constants there, and these things need a little jazzing up yet. Like this could use some borders before I put it in. You might monkey with copy paste it onto a Word document so you can see how wide it is, how it will look on when you paste it in, so that it fits nicely. We have a graph, the calibration graph needs to be jazzed up. I got started there, and these equations couldn't hurt. They're in your lab the lab manual. And explain what's going on. Explain that we've set this up, so we have this equation here, and we're looking for the E1. We're going to monkey with NF and NI until we get E1 to be the same each time, and then we do since we have multiple measurements of the same thing, we take our standard deviation of the sample and our standard error, and then we can get ourselves a fractional error, and that's used to compare to, it's a basis for comparison. So for example, the actual value, of course, we don't expect any error, and the most obvious one is the comparison here. Now, the other thing, though, that says we did a good job, 5%, as long as we have a plus minus at the end of the day, the standard error that's less than 10% of the number we measured, we've done a good job. And it doesn't necessarily prove the formula. We need to, let's think about this. Well, no, that's part of it. I suppose we could do an R-squared test. There's other tests we might do, but for now, this is just about learning a little bit about calibration, and then setting things up so we could, even though we have different energies of the different lines we looked at, how we can set things up so that we have an expected answer that's the same every time. And so that allows us to do some analysis. Okay. So, well, I got to subtract out a little bit, but this is getting a bit long, so I'll make another video about the final logbook.